Check this out. I have two clear colorless solutions over here. Let's pour them into each other. We pour the first one and we pour the second one, and boom, we now get a white color solution. Here's another example. Again, two colorless solutions. We pour one into another and boom, we again get a beautiful yellow color solution. What's going on over here? To find out, let's dig a little deeper. Here's a more curious question for us, okay? So in the first case, what did we do? We poured sodium chloride and silver nitrate together, and that gave us a white color solution, right? But now, if I were to change just one element, instead of silver, if I had potassium over here, everything else is the same. So if I had poured potassium nitrate and sodium chloride into each other, I wouldn't have gotten anything. I would have just gotten a colorless solution. It's not that interesting, and therefore I couldn't find any footage online. So this is just an edited image, but you get the point. We wouldn't get anything interesting over here. But the big question is why? Why silver nitrate and sodium chloride gives us a white colored solution, whereas potassium nitrate, just one change, and sodium chloride does not give us anything? Let's look at it. Let's look at it one by one. So in the first case, we are reacting sodium chloride aqueous solution with silver nitrate aqueous solution. What do we get? Well, remember that in aqueous solutions, ions usually dissociate. So over here, we'll get basically Na plus ions and Cl minus ions. And over here, we have Ag plus ions and NO3 minus ions. So when I pour them together, we just get all those ions together, okay? Now, because these are together, they can form new combinations. Of course, cations should always combine with anions, okay? So Na can now combine with NO3. But there's nothing special because, again, they will dissociate. But Ag can also combine with Cl. When Ag combines with Cl, something interesting happens. What? Well, guess what? AgCl is insoluble, and therefore it will precipitate out. And that's the reason why this whole thing looks white, because of the AgCl precipitation. So what do we end up with? We'll end up with AgCl, which is insoluble. So that's why it's written as solid over here. It precipitates out. So let me just shade over here to show that it's precipitating, okay? And what remains in the aqueous solution? Well, sodium ions and nitrate ions. So we get sodium nitrate aqueous solution. The white color is due to the AgCl precipitating out. Now, if you zoom out and look at the reaction, see what has happened. Sodium and silver cations have switched places. Sodium has replaced silver over here to get sodium nitrate, and silver has replaced sodium over here to give us silver chloride. So since there are two cations replacing each other, there's a double replacement happening. This is called, no surprise, a double replacement reaction. We can also call this double displacement reaction. So what we witnessed was a double replacement reaction, and one of the products precipitated, giving us that white color. Now, before we look at the other one, a quick question for you is, can you identify which of the elements underwent oxidation and which ones underwent reduction? Pause and think about this. Okay, whenever I want to think about that, I just look at the charges on the elements. Well, over here, sodium has a positive charge as a cation. On the other side, well, it's still a positive cation. So no change happened to the charge on the sodium, nothing happened to it. Okay, what about Ag? No change. The same is the case with the anions as well. No change, no change. Which means, look, nothing is undergoing an oxidation, nothing is undergoing a reduction. So double replacement reactions are not redox reactions. And you may be wondering, Mahesh, why are you excited about the fact that it's not a redox reaction? I'm excited because I used to think that all chemical reactions involve must involve electron transfers, and therefore all chemical reactions should have something oxidizing and something else reducing. But I was wrong. Look, right in front of our eyes, we can see examples of chemical reactions where there are no electron transfers, where there is no oxidation or reduction. So that's pretty cool. But anyways, now let's look at the other one. What happens when I pour these two together? Well, let's look at the reactants. This time the reactants are NaCl and KNO3, both are aqueous solutions. I pour them together. So just like before, I will now have all the four different kinds of ions over here. Na can combine with NO3. Remember, cations can only combine with anions, okay? Those are the only new combinations you can form. So Na can combine with NO3 minus, but again, it'll dissociate. K plus can also combine with Cl minus, but what's important over here is that KCl, potassium chloride, is soluble. Therefore, when K and Cl combine, again, they will dissociate. So nothing happens over here. There's no precipitation. I'll just end up with a solution where all the 4 different kinds of ions are just floating around together. So no chemical changes happened. And that's the reason why I don't get any colorations. I don't get anything over here. So over here, I get essentially no reaction. So you notice the key difference? The key difference was AgCl was insoluble. That's why it precipitated out. And that's why in order for us to get a double replacement reaction, we need one of the products to precipitate. If both are soluble and they form aqueous solution, then nothing will happen. We'll just get a solution with all the 4 different kinds of ions, no chemical change at all. So in general, we can now write down what a displacement reaction looks like. We can say that if you have an aqueous solution of AB reacting with an aqueous solution of CD, then in a double displacement reaction, the 2 cations replace each other. So A will now combine with D and C will combine with B, but that will only be the case if one of them is insoluble and it precipitates out. Precipitation, is the key to having double replacement reaction. So look, if you pour any 2 aqueous ionic solutions, do not expect to get a double replacement reaction. You'll only get them if one of the products is insoluble. But now we'll be wondering, how do we know whether a particular salt is soluble or insoluble? I'm glad you asked that question because that brings us to the solubility chart. A solubility chart is basically that. It tells us whether a salt is soluble or not. So here's how we can read it. If you want to look at potassium chloride, here's potassium cation, here's the chloride anion, and now we can just say, hey, this is where they meet. And so this is the solubility of potassium chloride. And you can see it is soluble. But what about silver chloride? Silver is here. Chloride is here. Well, again, try to make them meet. And what do you notice? Silver chloride is insoluble. And what about this yellow, slightly soluble? Well, don't worry too much about that. We'll only work with the soluble and the insoluble ones, okay? And just by looking at this chart, you can see some trends. For example, you can see salts of lithium, sodium, potassium, and even ammonium, almost all are soluble. Of course, there are some exceptions, but they're all soluble. In contrast, salts of lead are almost insoluble. You can also see salts which have nitrate ions and acetate ions pretty much soluble. Anyways, now equipped with this solubility chart, we can predict whether certain double replacement reactions are going to happen or not, okay? So let's check that. Here's the first one. We're going to pour lead 2 nitrate aqueous solution and potassium iodide aqueous solution together. What will we get? Pause the video and try to do this yourself. First, think about what the potential products are by swapping the cations, and then check whether one of them is insoluble. If it is, then it'll precipitate out, we'll get the reaction. If both are soluble, we'll get nothing. So pause and try. All right, here goes. So one of the potential products is lead combines with lead cation combines with iodide ion. So before writing, let me just check over here. Where is lead? Lead is over here, and iodide lead cation, okay? Iodide is over here. So if you look at that, hey, there you go, it's insoluble. So I know immediately lead iodide, and I need to be careful. Lead has a +2 charge and iodine over here has a -1 charge. So to compensate, I have to put 2 over here. So I get lead 2 iodide. That is insoluble, so that will precipitate out. And what else will I get? Well, potassium can combine with nitrate. And again, we can check for it. Where is potassium? Potassium is here. Nitrate is over here. So if I go down, go over here, look, it's soluble. So I'll get potassium nitrate, which is soluble, charges +1, -1. Okay, so I'll just get this. So I'll get an aqueous solution. And of course, I'll have to balance it out. Let's quickly do that. So I have 2 iodine over here. So I'll put a 2 here. So 2 potassium. So I'll put a 2 here. And that balances everything out. And this is the experiment that we saw earlier. We are pouring potassium iodide into lead 2 nitrate. What is that yellow color? That's basically the lead 2 iodide being precipitated. And now the aqueous solution contains potassium and nitrate ions. All right, why don't we try another one? This one looks a little bit intimidating, but the idea is the same. So why don't you pause the video and try this again? All right, we start by thinking about what the potential products are. How do we do that? We swap the cations, okay? So ammonium cation will come, let's combine them with the acetate ion. Again, before writing it, let's just look over here. So where is ammonium? Here's ammonium, and acetate is over here. So let's look at that. Oh yeah, that is soluble. So this one is soluble. The other one would be sodium and sulfate ion. So sodium is here, sulfate is here. What do we get? Oh, that's also soluble. Nothing is insoluble over here. What we'll get is soluble, so nothing precipitates out, which means we'll just end up with a solution where you have all these 4 kinds of ions. So that means we will get no reaction. All right, so the final thing is that there's a special kind of double replacement reaction, which we call acid-base neutralization. Now we'll talk about what acids and bases are in detail in future videos. We'll look at all the cool properties and everything, but for now, think about acid as basically an ionic solution which has hydrogen cation and some other anion, and base as an ionic solution which contains a hydroxide anion and of course some metal cation. For example, consider HCl, which is an acid because it has a hydrogen cation, reacting with sodium hydroxide, which is a base because it has a hydroxide anion. What will happen? Well, we just swap the cations. So sodium will combine with chlorine to give me sodium chloride, and that is soluble, so I'll get an aqueous solution. But the interesting part over here is what happens when hydrogen combines with OH minus? What do we get? This is no longer an ionic salt. This is H2O. This is water. Water is covalently bonded, so we now end up with a covalently bonded molecule. So we'll get water, H2O, and since it's no longer an ionic solution, we just write it as liquid. So look what we get in general. When you combine acid with a base, they neutralize each other to give us a salt and water. So this is a special kind of double replacement reaction because there are no precipitates over here, but the reaction happens because we get a covalently bonded liquid water.